Hello. Have you ever thought about the mathematics that goes into describing a falling object? This ball, if I want to predict the height of the ball as a function of time, I can use a pretty simple formula from algebra. And if I want to know where that formula came from, I can use calculus. But if I use that formula for this paper cup, it doesn't work so well. We need differential equations for that situation. So overall, in this stage of the modeling process called build the model, we're going to be interested in what sort of mathematics will we need to solve the problem. But before we jump into specific examples, there's a little bit of terminology we should learn first. The first terminology is continuous versus discrete. So most variables can be categorized in one of these two areas. And just to give an example, take a carbon dioxide level in a room. Now, what's interesting about that is it's changing continuously over time, but this sensor only records it once every 5 minutes. So it's a discrete data set, but the variable itself is continuous. On the other hand, population for a country, census data, is once again going to be discrete. And in some ways, it's changing continuously, but it's harder to see that because people are only born one person at a time. So don't worry too much about the distinction. Some models are based for continuous data, like differential equations, still work when you have a scenario where you only get data in discrete time intervals. And vice versa, I can use discrete models like simulation or difference equations to model data that is actually changing continuously. The second thing to talk about is interpolation versus extrapolation. This is useful when we're looking at data and making predictions based on that data. So to give an example, let's say I have a x-axis here where my independent variable ranges from 2 to 6. And I have some data here that looks something like that. And I draw some sort of trend line, some sort of model that fits that data. And I want to predict that that trend is going to continue either in the future or in the past. That would be an example of extrapolation. So even though the domain of my independent variable is 2 to 6, if I can, or if I plan to make predictions beyond 6 or before 2, that would be extrapolation. On the other hand, interpolation would be if I wanted to make predictions in between the data points, say at 3.5 or 4.5. The next thing to talk about is the type of model we might use, data-driven versus theory-driven. So data-driven, which is also known as empirical modeling, is just what it sounds like. It focuses on the data. So we don't really have a good reason for our model that we come up with other than it fits the data. It's not so good for extrapolation usually. It's harder to make a prediction when you're just basing something on data, but it can still be a useful tool. On the other hand, theory-driven, you may not need any data at all. Sometimes in physics, we can find a theory-driven model, like that free fall equation can be based on theory alone. But the best models are probably going to be a combination where hopefully we have a theory-driven foundation for our model, and then we collect some data to either solve for some parameters or confirm that we have the right choice. Next is accuracy versus precision. Those words are used interchangeably a lot, and there is some overlap between them, I suppose. But the key here is that accuracy is more talking about how accurate your measuring device is. Is it close to the true value? While precision is more talking about how close together the measurement values are. So for an example, assume we are measuring a 50-pound pumpkin. Something that was accurate but not precise, a scale that is, say, accurate but not precise, might measure 48 pounds, 49, 51, 52. So a couple of pounds off, but at least it's all around 50 pounds, the true weight. If something was precise but not accurate, you might get 54.2, 54.5, 54.6, and so forth. So all these numbers are really close to each other, but they're not actually that close to the true value of 50 pounds. Now, of course, we would rather a measuring device be both accurate and precise at the same time. Sources of error is another thing to think about when building your model. So there's lots of sources of error, but for now we're just going to focus on the main categories. The first category is formulation error. So this is when you make assumptions for a model, when you build your model and you just don't maybe make the perfect choice for it, there's going to be formulation error. This is going to be the hardest to quantify, but it's also going to be one of your probably bigger sources of error, and it's good to be aware of it. Another source is round-off error, which is just what it sounds like. If you have calculations from a calculator or spreadsheet and you only use 1 or 2 decimal places, that's going to introduce some error. Most of the time we can solve that just by using more decimal places, but we don't always have that luxury, especially if we need something that's really, really precise to get a useful answer. The third category is what I would call measurement/data collection error. For example, this CO2 sensor, even though it gives an output of 637, I don't know for sure that this device is so accurate that I can say it's exactly 637. There's usually some sort of error built into this device, and if you get two side by side, you'll see that actually they can be 10, 20, 30 parts per million different from each other, even when they're side by side. So that would be an example of measurement error. Data collection error is a little more broad. Maybe you're doing a survey, trying to get people's opinions on things, and you write down a wrong number, or the person lies to you, or you have a bad sample in some way. So there's more ways to get data collection error. The good news about these is that measurement error, hopefully we have a feel for how accurate our measuring device is. If you're using a ruler, you should hopefully be within a millimeter, as long as it's a simple thing to measure. Data collection, hopefully we can be careful about how we collect data so we get an accurate measure of whatever we're interested in. On the topic of error, it's good to be aware of the terms absolute versus relative error. So let's say we're given some actual value we're trying to estimate. So we'll call that X actual. All right, maybe it's the population of the United States in the year 2020. All right, there's some actual value. All right, and I come up with an estimate. And so, maybe I have a model where I am trying to compare my model's prediction to what I believe to be the true value. And so we compare those two numbers, and the simplest comparison is to just do the absolute error. So the absolute error is just X actual minus whatever my estimate was, which I'll call X of estimate. Now, the problem is that may be helpful in general terms, but if I'm trying to compare, say, I'm modeling the population of the United States versus the population of just a city in the United States, well, being 10 million people off for the whole country might not be so bad. Being 10 million people off for the population of Kansas City would be terrible. So what I really need is a way of compensating for that, and that's relative error. And relative error is the same numerator as absolute error, X actual minus X estimate. an absolute value, but I divide by x actual. All right, so this is the relative error, and then that can be expressed either as a decimal, or if you prefer percentages, you can express percentage error, which is just converting this number into a percentage. So that's a little bit of terminology. We'll get into an example in the next part of this video. We'll see you then.